Okay, so welcome to the second lecture. Apologies for the delay. So we wanted to make sure that hopefully this time we actually get the proper recording working. Before that, it was only the camera and not the slides, and that's not very useful. We'll fix and update the recording from Tuesday very, very shortly, and we'll get it up probably on the weekend. But there was ICML deadline yesterday, so everybody was a bit busy. Okay, so two things that we didn't quite cover on Tuesday. One thing was NDArray, because some people ask me, memory allocation and all of this, and I'll walk you through the details for that. The second thing is, as it turns out, not everybody has an AWS account just yet, right? So I'll walk you a little bit through how to launch machines on AWS, because I had a couple of people coming in office hours and asking how to do it, and I'll walk you through the details of how to launch things. And yeah, apologies, I've got a bit of a cold. So we did the linear algebra part on Tuesday. Today we'll dive a little bit more deeply first into how those vectors are actually stored in MXNet. So quick review here. Well, a scalar, that's just a zero-dimensional array. Vectors, a one-dimensional, two-dimensional array might be rows of features. So for every observation, you have a row of attributes. Now, 3 dimensions, well, you can get it by having a black and white movie. Or you could have, for instance, a color image. And in that case, you have, maybe, your 1024 by 768 pixels resolution, and then the 3 color channels. RGB, but you could have other color codings as well. In 4 dimensions, well, you could have many of those images. So the 4th dimension would then be the batching order. And if you want to push it further to 5 dimensions, well, you get videos, right? So I guess that should be all fairly straightforward and self-explanatory. It just gets supremely awkward to display this on slides beyond 5 dimensions, so we stop here. Any questions about tensors and arrays so far? Just what they are. So don't get scared if somebody tells you about math with tensors. They're doing very simple things and making it sound complicated sometimes. Okay, what we could do is you could create an array like a 3x4 matrix. You could fill it with any random entries. And part of the homework actually will be to create like a 4096 by 4096 array. So you can access elements as you would. I mean, this is basically exactly the same thing as you would see in Numpy. You can access an element. You can access a row or column. You can access a subblock by indexing appropriately, or then you can have indexed fields appropriately. So it's fairly straightforward. I'll walk you through this in detail. A couple of things. So we'll look at that in the Jupyter Notebook. So first of all, there are actually a couple of documentations. First of all, the NDArray chapter in our book. Then on the MXNet website, go to beta.mxnet.io. The search there actually works. You can look at the crash course for NDArrays. You can also look up functionality there. If you're not super sure about linear algebra, Gilbert Strang has a very nice class. You might want to revisit this. Unfortunately, we don't have enough time to cover it in a lot of detail, but if you're not quite sure about linear algebra, you should probably do this anyway. Some people asked about, how are GPUs designed and TPUs and, CPUs and how they all relate to each other and other accelerators. This is actually, again, a little bit beyond the scope of this class to go into it in a lot of detail. For now, essentially think of GPUs as a device which allows you to perform large numbers of linear algebra operations very, very cheaply. And to some extent, the purpose of a deep learning framework like Gluon is to shield you from the nitty-gritty of actually having to write CUDA code. That increases your productivity probably by a factor of 10 to 100. If you still care about details, there's actually a nice graduate level class an HPC course and look at the slides on GPUs. I think they are quite accessible even if you're not enrolled in a PhD program just yet. Lots of pictures, actually very nicely explained. Go through this. This might give you a bit of an idea of what makes GPUs special. Okay. So with that, let's look at some notebooks to see whether this works. Okay, just don't. And here's NDArray. Let's just run everything. Okay. So the first thing you would do is you would import, the deep learning framework of your choice. In this case here, it's MXNet, and we'll import NDArray as ND, just because it's supremely awkward otherwise to type it all the time. And the simplest thing you can do, and we covered that last time already, is you can just create a vector of numbers going from 0 to 11. So it's the equivalent of the range command, just that it's called arange. That's a vestige from Numpy. And you can ask what the shape is, and if you were to type in x.shape, you'd get 12. And if you were to type in x.size, you'd also get 12. The reason being that x.size counts the total number of entries. X.shape will give you, for instance, if it's a 3x4 matrix, it'll give you 3,4. And if it's a 12-dimensional vector, it'll give you 12. So then you can reshape things. That's exactly what we did here. And let's actually just do this. And there you go. If you print now x.shape, it'll return 3,4, because that's exactly the shape that you gave it. Right. Whereas if I were to execute print x.size, it'll tell you 12, which is what you would expect. Now, if you wanted to reshape it into something that has 3 dimensions in the first, and you don't care about the rest, you'll just write -1, and this makes sure that you don't have to calculate all the dimensions, and you basically let the framework do the rest. So if you do that, nothing changes because Gluon is smart enough to figure out the rest by itself. Okay. Now, a couple of things. If you run nd.empty, it'll just effectively do a malloc, right? It'll grab some part of memory, and if that memory is uninitialized, there'll be whatever there is to it, right? So in this case, we got lucky, it's all zeros, but you could have arbitrary stuff in there. So only do that if you're really sure that this is what you want and that you're going to overwrite it with something sensible right away. Do not run NDEmpty, because this, and then just assume that they're all zeros. This would be a wonderful way of introducing bugs in your code. It would be something of a Heisenberg where maybe in your debugger you don't even find it because it might actually give you clean memory or not. So really think of this as malloc. The much more sensible thing is to allocate zeros. In this case, you know what it is. If you wanted to allocate ones, you could do that too, which is here, right? nd.ones will give you ones. This is all fairly straightforward. And if you have a specific array, it doesn't quite show up on the screen entirely. Let's fix that. you can specifically allocate an array by just specifying what should be in there. This is how you can call the constructor. Okay. We might want to generate a random entry. As a matter of fact, that's part of the homework. So NDRandom normal will give you a normal distribution entries, 0 mean, unit variance, and 3 by 2, sorry, 3 by 4. Right. So if I were to run this again, the entries would look obviously very different because, well, it's a random number generator. I can do all the usual operations with it. So I can add, subtract, multiply, and divide. I could even exponentiate. So let's do that. And unless we have something weird. Okay, there we go. This is now x to the power of y. Right, this operates on the entire array. Any questions so far? Hint? That operation is something that you'll need for one of the homeworks. Okay. The other thing that you'll need is the broadcast operator. Okay, so also exponentiation can work this way, sine, cosine, a lot of other functions. Now, of course, you can write a dot product. And so, for instance, you have, a 3 by 4 matrix, and then you have, this another 3 by 4 matrix, and you take an inner product. And since you have that transposed, so x dot t is the transpose, you'll get a 3 by 3 matrix out of it, which is very unsurprising. This is exactly what linear algebra would suggest. Just again, word of caution. Only if you invoke dot, you're going to get matrix or matrix vector or whatever products. If you just write the star, you're going to get element-wise multiplication. So this is different from MATLAB. Be careful. So our star is the MATLAB dot star. Right? Our plus is the MATLAB dot plus, and so on. You can combine multiple NDArrays. Well, it's very straightforward. Well, you concatenate them, and if you do that, well, you get different objects out of it. So I should probably be printing this such that you can see the difference. And that didn't work because I probably messed with x and y before. That's why. Yeah. So what I did before is I reshaped x. So now I'd have to figure out what the shapes of x and y are. Let's see. Okay. And yeah, of course, in this case, if I concatenate them, since it's only a one-dimensional vector, the second thing doesn't make any sense. But that's just because I didn't set up a. So this will work just fine. So you can concatenate vectors, which is boring, but you can do that for any array. Any questions so far? I mean, this should all be, yes?
What's the best way to add like a second dimension to make it 4 by 1 instead of just 4 comma?
I could do this. I could, so I could, for instance, have x. 4,1. I think that will work. Shape equals probably. Now I would of course have to do the same thing for y. And so there we go. And now if I were to concatenate it along the second dimension, what do you think we are going to get? Okay, I'll get a 4x2 matrix. No, I actually get an error.
You need x equal to explosion shape.
Oh, yes, of course I do. Yeah. Yep. And now if we do this. Yep. So, turns out it's quite easy to be stupid in front of your laptop. Okay, good. So then we can do other things. We can, check for equality. And this way we get another matrix out of it, which just checks the entries. And if x and y were matrices before, you'd get this. But since I overrode this before, I'm not going to re-execute this code right now. As in, if we did this, we'd get probably lots of zeros out of it. You can use that for indexing and other things. You can sum over things, right? That's fairly straightforward. You can sum along certain dimensions. Again, for the very details, please also have a look at the NDArray documentation on the MXNet website. So go to beta.mxnet.io. There's the very specific call signature, but it's fairly straightforward. Then the last thing is, of course, sometimes you want to move back to Python land, so you can just convert things as scalar, and that turns things into that. Right. So if you were to print then in one case you'd see an NDArray, in the other case you would see the number. And right. So it's the same value, but it's just in one case it's an array, in the other case it's just a single number. Okay. Good. Now the infamous broadcast mechanism. Let's say I have a 3x1 matrix, or aka a vector, and I have a 1x2 object. So then, okay, so that's what they look like. So if I wanted to, multiply or add or do something with them, then what the broadcast mechanism will do, and it's important here that the number of dimensions are the same, right? It'll just replicate things according to the dimensions, right? So if I were to combine them, a plus b, I'll get the 3x2 object where the first and the second entry respectively are repeated. So the easiest way to think about what that means, it's like an outer product in linear algebra. So remember we have, you have the inner product x transposed y, but if you have y times x transposed, right, then rather than a scalar you get an entire matrix, and except that for only multiplications, which is what you do in linear algebra, you can do that for a lot of other operations like addition, exponentiation, or whatever. And this is a very quick way of generating large objects without a single for loop. So that makes your life easy. This is probably the conceptually hardest thing of all of this. Okay, any questions here? Okay. Well then, let's move on to indexing and slicing. And that does exactly what you want. It picks out the appropriate rows. And you can, read things. You can write them as you would expect, right? And you can do that for entire rows or columns. So for instance, here I pick, the first 2 rows, all the columns, and set them to 12, and it does exactly what you would expect it to do. Okay. Now, here's where it gets a little bit more interesting, right? So, suppose I do this. Then, okay, so I can look at effectively the pointer that Python has to y. And if I write y equals y plus x, then, well, the pointers before and afterwards are different. We could actually print this out, just in case you're curious. And so you'll see that, the references are different. So what's happened is basically Python went and, in this case, MXNet, went and took the memory locations for x and y, added the values together, put this into a new location in memory, and then this was assigned to y, and then, of course, the rest gets dereferenced and is gone. But, yeah. That's not a big deal if you have, 5 by 5 matrices. It's a huge deal if that matrix uses half of your GPU memory, because you may run out of memory before you can even compute this. Okay, so we need some fix. So one thing you can do is you can simply say that explicitly you want to assign the outcome x plus y to the location z. And while this is kind of a notational convention, but that's basically what you get. By z colon, you say, well, I want that memory location, and then MXNet will happily write into that location again. If you do that, well, you get the same pointers. There's a useful other function. It's called zeros like, which basically means create another object with the same shape as y, but with all zeros. And this is often useful if you want to have, for instance, weights that match, some data or something like that, and you automatically want to make your code smart, such that no matter what input you throw at it, you get the right weight vectors. You can initialize the weight vectors with zeros like or ones like or other tricks like that. Okay. Now, this is kind of nice, but it's still not quite nice, because what it actually does is it allocates memory first to compute x plus y, and then it assigns it to z, right? So this is still going to use about twice as much memory as it should, right? We should be able to do all of this directly in place. So the way how you can do it directly in place is you essentially invoke things like element-wise add and so on, and those operations force MXNet to be very, very memory efficient. So I'm mentioning this because this will be useful for your homework. Okay. And with that, we are almost done. The last thing is we can use plus equals, so that makes it a little bit nicer to use. So that actually takes care of a lot of these operations. Okay, last thing, you may sometimes need to move code from, or data from Numpy to NDArray and back. For instance, you might have some data loader code, some preprocessing code written in Numpy or SciPy, and then once you have that data, you want to push it into MXNet and process things. And so it's very simple. You just execute as Numpy, or you invoke the constructor with, the Numpy element there. Question for the programming languages or Python experts among you: why can I not invoke simply the numpy.array of x? Why can I not say a equals numpy.array of x? Why can I not invoke the constructor with the MXNet argument, with the NDArray argument? Yep.
Because NumPy-arrays expect.
You're spot on. So NumPy has absolutely no idea of what MXNet is. So why should it have any idea of what to do with an NDArray object, right? And so our poor NumPy is completely out of its depth when it gets a weird object, so we need to make it easy for NumPy, and that's why we need to provide that functionality in NDArray. Now, one important detail there, as you do this, basically the world stops, right? So, or rather at least Python stops, and nothing else happens while Python is busy moving things from MXNet land to NDArray land or vice versa, to NumPy land and vice versa. Now that's not a big deal if you do this once or twice, but if you have an entire vector, this will slow down your operations a lot. And one of your homeworks is going to be to measure exactly how horrible this is. Now before you think that this is trivial, data point, somebody who just this year became assistant professor at a very nice university essentially made this mistake a few months ago, and then he came to me and asked, why is my code so slow? Right? So it's one of those bugs that are obvious in hindsight, and this is the case not just for MXNet, but you would run into similar issues with basically PyTorch or TensorFlow and others, essentially because those behave essentially like a foreign world to Python, and therefore converting data between two different systems like Python and essentially the deep learning framework will trigger a global interpreter lock, and then you run into trouble. Okay, so you want to minimize that. Any questions so far? Yes?
Why don't you just throw an error when you try to do ND.array? Oh, that would be.
No,
That would be on NumPy's end.
So basically ND.array will actually do the right thing because we added that functionality to NDArray. Right? So because the NDArray constructor can take NumPy as arguments. But the converse would require a modification on the NumPy end. Okay. So with that, let's look at something